Morning, everyone. Morning. How are you doing today? All right. So we finally get back to the controls. Okay. So we learned about linear algebra. We learned about different systems, how you represent systems as impulse response, transfer function, and so on. But now we get back to modern control. And today I'll be talking about representations in state space, which is the basis for all of that theory. And we will see how it connects to all of the previous lectures. And we will see also what are the relations between state space and transfer function and ODE and all the other representations that you saw so far in that course and before that course in signals and systems or control systems courses that we took before that, right? So again, to repeat the motivation for getting into state space was invented in probably before 60s, but became very popular in 60s because of the space program, because all of the satellites and all of these new space programs, which were new back then in 60s, started with that theory. It was not possible to do anything with transfer functions and classical control theory. It was not working well. And it was not generalizable very easily to MIMO systems, which is multiple input, multiple output systems. And satellites are definitely multiple inputs and multiple output systems. So controlling that type of systems was too complicated and black magic type of stuff. So people struggled to understand how to control these things. There was practically parallel development of control systems, which was completely independent from transfer function and classical controls. So classical controls and frequency methods and all the things that you learn in the first course on controls were developed typically in the West. All of the state space control was developed in the East, and I'm talking about Soviet Union at that time, okay? So this was completely parallel, independent development of control systems because of the curtains that they had, like iron curtain, right? So they never communicated to each other. So they developed in completely different way and started with original differential equations and developed that from differential equations up to all of the theory of state space control. And only in 60s, this started to leak to the West. And West very urgently actually gained momentum on that and started to develop a lot of different things. And this is why you see all of these publications suddenly popping up from 60 and forward in the West literature, because they had no idea that this was developed for 50 years in Soviet Union, okay? And then they had Congress in 60, actually this is the year where it all started, when Moscow invited all of the scientists from the West, first time, actually let them into Moscow to the Congress of Controls to show them that stuff, okay? And this was the breaking moment where everything started to change and everyone started to move toward modern control, all right? So this representation of state space that we are talking about is completely equivalent to ordinary differential equations, which means it has initial conditions, it has all of the differential equations, it's just list of n differential equations instead of one equation with n derivatives. This is the difference. Now, as I mentioned, it's almost same design for SISO and MIMO systems. Single input, multiple input, output, whatever. Same idea, same design, same formulas, same theory, okay? They're not changing much. Just dimensions of the matrices are practically changing. Everything else is staying the same, the formulas are the same. You can do the same analysis with Z transform and with S transform. This is how Z transform was actually developed to match same kind of properties of S transform. So all of the analyses are almost the same for discrete time systems, which are in the computer, and continuous time systems, which are more realistic systems, physical systems, which are working somewhere. All of the controls for optimality, robust control, optimal control, and many parts of nonlinear controls are based on state space. So this is important to learn that basic knowledge about how state space representations work. And also you can design nonlinear systems with that type of control, partially nonlinear systems. It's almost the same, okay? Very different from classical controls where it becomes very complicated connection between linear and nonlinear, and what you do, how you separate it into transfer function, plus some nonlinearity in series or in parallel, or you have multiple different ways to represent it. But here it's kind of more straightforward. So this is the type of equations that we'll be talking about, and I'm talking about linear time invariant systems and linear state space representation. So this is the equations that you will have. First equation will be x dot, which is vector of x's, x1, x2, x3, all of them dot, equals some matrix A times vector x plus some vector of matrix B times vector of inputs u. And they are obviously functions of time, each one of them except matrices A and B. Now, the output of the system is also some matrix of vector C times vector X. So for CISO systems, it will be like row vector times column vector, okay, which is just number, plus some number D times U. And D could be number for CISO systems, or it could be matrix for MIMO systems. But formulaically, it will look exactly the same in terms of formulas that we will be using, okay? So it doesn't matter if this is color or some sort of vector or matrix, okay? In formula, it will look exactly the same. And this is more explicit representation. This is how you write these equations, and we will work with that system of equations all the time. Okay, so you just need to memorize how it looks like. And we will work a lot with CISO systems. So this is example of CISO system. I will show you examples of MIMO systems later. So you have square matrix A, which is n by n, and n is order of your system, which means that this is the highest derivative in your ordinary differential equation, if you wish, if you represent it that way, or number of poles of your system, if you represent it as transfer function. So this is n. So it's n by n A matrix with all kinds of coefficients. You have n by 1 vector B, which multiplies that variable u, which is scalar variable u. It's a function of time, right? And to find y, you do some vector C, is n numbers, and those are constant numbers, times vector x plus du, and d is scalar. D is just number, right? Because the dimensions should fit. So y is 1 by 1, the scalar function. All of them are functions of t, obviously. Like y is function of t, x's are function of t, u is function of t. But everything else is constant. All of the a, b, c, d are constants. All of the coefficients. Any questions so far? This is, I'm just writing that matrix equation explicitly. Same thing. It's exactly the same for CISO case. Okay? The upper line is for any case. It's CISO or MIMO. But this one is CISO system. And this is how you represent that with blocks. So I showed you already example online. I published example online how you develop block diagrams for any given system in state space. Okay, you're just drawing all kinds of integrators and so on. But here we want to combine multiple integrators in the same block. And we can use that type of block, which is x dot equals ax plus bu. And this block generates vector x. And by bold line, I define vector instead of scalar, right, for the CISO system. You also have input of x0, which is here, right? The x0 is initial conditions. Typically, I will never use that again, which means I will assume that this exists implicitly, but I will not draw that arrow of x0. You just need to remember that it is there. Like that arrow here, I will never use it anymore. This is the last time I'm actually showing that arrow here. You just need to know it exists, okay? It's entering the system, you have initial conditions. To solve that equation, matrix equation, you obviously need to start somewhere, right? So to solve that thing, you need to start with some initial conditions because you have derivative. How would you compute derivative without having initial conditions? You can't, right? So you have them. But I will just skip that for simplicity of representation, right? I will not mention that every time that the system of equations plus initial conditions, okay? I will just ignore it, kind of. Now, so you have input u and output x of that system, which is that first system of equations. That x multiplied by c, which means that arrow shows that I'm taking vector x and making dot product with vector c. So when you're making dot product with vector C, you obviously get scalar number, like 1 by 1 vector if you wish, okay, just a number. So this number is added to U times D, and this is amplifier. This triangle shows amplification by that number D. So I'm adding du, which is that thing, plus C times X, and then I get Y. So this is the system that you can think about as a transfer function. So that entire thing is your transfer function. Okay, that entire thing from U to Y. This is your planned part. Okay, this is your actual open loop system. There are no closed loop here, no feedbacks, no nothing. This is just representation of CISO system as is. Any questions? And pay attention that all of them are functions of T. Yes. No questions on the representation here? All right, you have another representation as well using integrators, but this is vector of integrators. Pay attention that if I'm drawing something like that and you have vector input and vector output, this means that you have multiple integrators, M integrators in that particular loop. So what I'm trying to represent with that system, it's completely equivalent to that thing. I'm just opening that box. Okay, so I'm adding that box. Pay attention that this part stays as is. So you have it here between X and Y and between U and input, right? But I'm opening that box and implementing that like that, which means X dot, which is the input to that integrator as vector, this vector of X's, X1 dot, X2 dot, and so on, equals to B times U, which is that vector, plus A times X. That's exactly what the thing says. And you can implement that in Simulink that way, or you can implement in Simulink that way, or you can implement in Simulink in multiple other ways, or you can do that like integrator by integrator. But Simulink accepts vectors as inputs to integrators. So if you put block of 1 divided by S, it will accept input of multiple X's. So you'll be able to simulate the system like that. So this is one possible way to represent it in Simulink and MATLAB. Okay, any questions on that? These are just different ways to represent the system as block diagram. Yes.
So I'm not sure I understood the difference between the thick vector lines and the thin ones, because both of them are.
So thin line is single function, not vector. It's like function of time. It's like signal, which is one dimensional. And like thick lines are vectors of signals, which is like multiple signals which are moving on the lines, multiple lines.
So anytime you.
So here you have X1, X2, X3, X4, and so on.
And if,
Depends on the.
U at the beginning there, if U was multidimensional.
Then it would be like thick line, yes.
Okay.
So in that case, it's a CISO system, single input, single output. So U is a function of time and Y is a function of time. And it's not multi-channel type of things, like single channel input, single channel output. But X is always multi-dimensional.
Can you go back one slide?
Sure.
Okay, you use the thick ones there too.
Yeah, so thick is for the vectors, okay, for B, for X, for that thing.
Thank you.
Any other questions? Okay, so how do we convert from state space to transfer function? This is relatively easy part because we have Laplace to help us, obviously. But if you're making Laplace transform of matrix equations, you're practically doing Laplace transform of element by element. So this is how Laplace transform works in matrices in general. You're just doing each element Laplace transform. So let's try that. You're making Laplace transform of derivative first. Just to remind you that Laplace transform of the derivative is S times F, Laplace transform of the original thing. So it's just multiplying by S, the original function. And then you have some minus some initial conditions, which is that add on to your function. Okay, this is how Laplace transform works for scalar functions. For matrix functions, it works exactly the same way. You just multiply by S every single element in the vector. Okay? And this is what you will get in that matrix equation. So I'm taking the first equation, instead of X dot, I get S times X. And this X is vector now. And if you remember our notation, right? We're using capital letters not only for matrices, but also for vectors if I'm adding S to that. So it's like vector of Laplace transforms. It's still capital letter. So I'm using X here as a vector. This is not matrix. This vector, which is X1, S, X2, S, X3, S, and so on. Laplace transforms of all of the states. Okay, this is a vector. But it's same thing, minus X0, which is still vector. So it's like X01, X02, X03, and so on. This is vector of X's. Here I'm multiplying by a constant matrix A, Laplace transform of the vector X, okay, plus B times Laplace transform of the function U. This is what you get from that equation, from the first equation. Same thing with the second equation, you're just replacing all of the variables with Laplace transforms of these variables. That's it. Everything which was function of time now becomes function of S, Laplace variable. Any questions so far? And this is where we go with that. If you look at the first equation here, you can move AX to the left side and X0 to the right side. So I want to put apart everything which multiplies X's on the left side and everything else on the right side. So this is just algebra, right? I'm just changing the sign, moving different sides. And I'm doing the same trick that I showed you previous time, that you can multiply by I here. So you can make Sx equal to Six, which is identity matrix. Remember the trick? But pay attention that when I'm adding the trick, you cannot separate Si, you can separate only Ix, because Si is not scalar, okay? It's not equal to S, but Ix equals to X. So when you separate, you can separate only I with X, right? But if you still keep the X, you can put together S and I. So this will be like S on the main diagonal, still will be matrix, right? So Si is matrix with S's on the main diagonal, right? This is what it is. Okay, so this is how it looks like. So when I move that thing to the left side, I can take Si minus A and take them out of the parentheses. I can combine them together and multiply them by X. Why? Because this is distributive law, right? This is that thing times X minus that thing times X. So this will be exactly the same thing. It will be Sx minus Ax, right? So this is what you have on that side. And on the right side, you have that X0 is positive sign plus Bu. Okay, so far? So we get that type of equation. Now you want to compute the actual state explicitly. You want to find the solution, what X equals to as a function of everything else, which is all of the matrices and input. So you want to write eventually, like to find transfer function, you want to write Y as a function of U, right? So you want on the left side to be something related to Y, and on the right side, everything else which is not dependent on Y, okay? But dependent on U alone. This is what you want. But Y is a function of X, right? So if I find X, I can then write Y as a function of X. So let's find X first, explicitly. Like what would be the result of X? This is our goal, right? Not to get the transfer function. So this is what we'll get. You need to get rid of that part, right? Which is Si minus A. How do we get rid of that matrix, which is Si minus A? We're just multiplying from the left by inverse of that matrix, both sides, right? And this is how we cancel stuff in linear algebra, right? We cannot divide it by that, but we can cancel it out if it is invertible, okay? Assuming that this is invertible, you can multiply both sides by inverse matrix. And then X will be equal to that inverse matrix times X0 plus that same inverse matrix times Bu, because we multiply both sides, the equation, all right? Now, practically, this is already the solution for X in Laplace domain. If you want time solution for the X, you just need to do inverse Laplace transform on that thing. And hint, if you want to do that, do you remember what that thing is? Which is called also resolvent. Very popular term, Si minus A inverse. We saw that in linear algebra, previous lecture. You saw that before, I'm sure. I showed that. This is actually Laplace transform of the exponent to the AT. This is what it is. We will see that in the next slide, but just remember that there are connections here. This is why I'm showing all of these exponents of matrices and other things that you saw in linear algebra. This is how it starts to connect together, trying to put some pieces together, right? So you can actually make inverse Laplace transform of Z. This will become exponent to the AT, and this will become exponent to the AT. And remember what is Laplace transform of multiplication? Or multiplication, what is inverse Laplace transform of multiplication? This is convolution, right? So you have two functions of S here. One is like inverse Laplace of Z is e to the AT, and inverse Laplace of Z is u of t, right? Practically, you'll get just convolution back here. So it will be convolution between the exponent of matrix times convolved with input, okay? So technically, this will be some sort of kernel or impulse response of some way of your system, right? But we'll get to that in the next slide. All right, so for y, it's very simple. Y is just multiplication by c plus du. This is all you need to do, right? So when you're computing y of s, you're just taking that formula for x of s, multiplying it by c from the left side. So it's c times z plus c times z plus du. That's it. So I'm done with the solution in Laplace domain. This is solution, explicit solution for output of any CISO system, or actually any MIMO system as well, because I haven't used anywhere that this is a system, CISO system specifically, okay? You'll have exactly the same solution for any system. But then this might be a vector if it is not CISO system, okay? You might have multiple outputs. So y of s will be multiple different y's. It will not be like single function. All right? But what we need to find transfer function is y divided by u, right? This is how transfer function is defined. Remember that? It's output divided by input. This is transfer function. If you have any initial conditions, as you remember, you cannot define transfer function. Transfer function is defined for 0 initial conditions. And this is why only for x equals to 0, you can define it. And if it is defined as 0, practically this is your transfer function. This is c times si minus a inverse times b plus d. That's it. This is what you will see. But you have also different names for different parts of that equation. It's important to remember that sometimes we are using that terminology as 0 input response, which means if u equals to 0, this will be your response. This is 0 input response, ZIR. And if u is not equal to 0, but x equal to 0, this is 0 state response, ZSR. And I assume you also heard the same terminology in Controls 1 course, probably. Maybe you don't remember, but people use 0 input response and 0 state response in Controls 1 as well for transfer functions. So 0 state response is practically that part, right? Any questions on the Laplace solution? And now we will move, obviously, to the transfer function, which is something that we wanted to find in the first place. We just take out that u out of the parentheses here and combining that part with the d. This is your transfer function. This comes directly from here. I'm just dividing, I'm assuming that x0 equals to 0 vector and dividing ys by us, which is transfer function. What is left? That part and that part. Any questions on the transfer function and how you get there? You're just using that formula. Done. So this is that simple. You're just taking matrices A, B, C, D, putting into that formula, you find a transfer function. This will be a rational function here, if you compute all of the things. Questions? You have equivalent representations for transfer functions and equivalent formulas. Sometimes they are, or many times they're actually easier to use than the original formulas that we developed. Here's one formula. You're using block matrices and you're computing ratio of two determinants. So this determinant is determinant of Si minus A. And this determinant is Si minus A block, then minus B block, C block, and D block. Pay attention that they also not rectangular blocks, because C is vector, D is number, B is vector like that, and Ci minus A is square matrix, right? Which means that for CISO systems, this matrix will be of order n plus 1, right? Because you're adding n by n matrix here block, plus single line of C here. So it will be n plus 1. And in that dimension, you have n by n matrix here, plus vector B, which is adding one more dimension. So if you have like system of order 3, this matrix will be 4 by 4. It still will be square, but n plus 1 by n plus 1 dimensions. All right? So this is bigger determinant to compute for your particular case, right? But determinants for lower orders are kind of easy to compute relatively. So this formula sometimes is easier to use. And why is that equivalent? Let's see. So let's simplify that. Just to remind you that in the block matrices part of linear algebra, I showed you that formula that if you have like 4 different blocks, you can compute determinant of that block matrix as that thing if that matrix is invertible. Okay, if that block. And pay attention that these are not the same matrices ABC that we have here. They are just names of the blocks. So this is our matrix A, which is here, the block A. This is block B, block C, and block D. All right, so please do not mix them, okay? This A, B, C, D are not the same like here. They are different A, B, C, D. They're just names of the blocks. So let's compute that. So we have determinant of A, which is det Si minus A. This is that block, okay? Times determinant of D minus, and the complicated expression. So D is equal to D here, minus C. C is still equal to C, so it's still C, times A inverse. So A inverse is that block inverse. So it's that thing which is called resolvent, okay, inverse, times, and finally you have block of B, and block of B here is minus B, right? This is a B block, so it's times minus B. So let's simplify that, okay? So minus will go here, so this will become plus, and you will have practically C times Si minus A inverse times B plus D inside of the determinant. This determinant will cancel with this determinant, right? They are just polynomials. Practically speaking, this is characteristic polynomial of matrix A. Remember that? This is just polynomial divided by polynomial. Same polynomial, you can cancel it. All right? And then you have that thing left. So this is what you get. So why is that thing the same thing like here? Pay attention that the only difference here is that I'm adding determinant here. So it's same formula, it's C times Si minus A inverse B plus D. But I'm saying that this thing equals to whatever you have sitting inside the determinant now. Why is that? The determinant of what equals to itself. Yes. So I got almost the same thing, almost, right? But I have a determinant standing in front of that expression that I want to get. Because what I want to claim is that this thing is the same thing as this thing, right? Which is sitting inside the determinant. This is my claim. Why? I mean, you can get rid of determinant only in one case. Yes.
Matrix with only one.
Hmm?
Like, does it make sense that it's a matrix with just one value?
What do you mean by one value?
Okay. If there's a matrix of size 1 by 1, it is like one element.
Exactly. This is scalar.
Yeah.
It's just number. Because all of that thing is just 1 by 1 matrix. All right. So determinant of 1 by 1 matrix is that matrix itself. Okay. And since this is one dimensional, the determinant of that one-dimensional thing is that thing, all right? That's exactly how it works. So this thing equals to the original transfer function formula that we had. And you have more formulas like that for simplicity. If you don't want to go to higher determinant, you can use determinants of Si minus A plus BC divided by the characteristic polynomial plus D minus 1 will give you exactly the same solution. And this is determinant of n by n, not n plus 1 by n plus 1. So sometimes it's simpler and easier, especially if D equals to 1. Very convenient formula. So you have multiple different ways to compute it. All of them are equivalent, giving you exactly the same solution. So you pick your favorite solution, okay, when you solve it. Now, this will not work for MIMO systems, because for MIMO systems, you will have multiple transfer functions. It will be a matrix of transfer functions instead of single transfer function. So you will not be able to do that skipping step, right? To say the determinant of that thing equals to the original thing. For MIMO systems, this will not work, okay? But previous formula will, because we haven't assumed anything on dimensions of the matrices. Okay? They can be any dimensions. Now we need to see something very important here. So pay attention that you have at the top, you have two polynomials practically, one polynomial divided by another polynomial. The bottom polynomial is determinant of Si minus A. And this is transfer function. And what is that polynomial? This is polynomial of poles. Right? You compute poles as roots of that polynomial. So I'm saying technically that that characteristic polynomial of matrix A is polynomial of poles, practically speaking. What does it mean? This is what it means. This means that actually eigenvalues of that matrix A are your poles. They are completely equivalent. So poles of the system are eigenvalues of the matrix A. And this is why we are talking so much about eigenvalues in general, right? Because all you need to know is like where your eigenvalues of your matrix A. And if you want your poles in closed loop to be in particular place, as we saw before, right? And we wanted them to be like to the left or in unit circle or like in trapezoid of some kind. All you need to do is to make eigenvalues of matrix in closed loop to be whatever you want them to be, okay? That's it. And then your poles in closed loop will be whatever you want them to be. And for that, we will develop controller design. How we can do that, we will see in the next week. But this is where we're going with that, okay? We are trying to connect eigenvalues of the matrix A to performance of the system in closed loop. And this is how we do that, because actually they are poles of the system. And we will compute closed loop poles of the system as well. Any questions so far?
Can you go to the previous slide? Okay, so in the last equation that we have for the transfer.
This one?
Yeah.
Mhm.
So like without knowing the dimensions of A, B, or any other matrix, can we directly comment that it will be a scalar matrix based on the dimension?
Only for CISO systems, it will be
Yeah,
scalar,
only for CISO.
yes.
Knowing
But
the
if, for
dimension-
example, D is matrix 2 by 2, whatever, you might have actually a matrix of G. So G will be a matrix of transfer functions.
dimension of D will define the number of elements or outputs. So
Yeah. Yeah. I mean, it will fit exactly all of these dimensions as well. I mean, the dimensions of this matrices also will define, but they need to match. Otherwise, you cannot add matrices which do not match, right? So in that case, dimensions of D will define number of inputs and number of outputs. Actually, dimensions of D will depend on number of inputs and number of outputs to match this number, right? Any other questions? Yes. All right, I mentioned already that name, resolvent. You have special name for that special type of matrix. And I mentioned before that this is practically a Laplace transform of the e to the at. So I want to find explicit formulas for x and y in time now. And I already hinted on how to do that. Right, so you have that x which you developed before. You're just making Laplace, inverse Laplace transform on both sides. And then you get x of t equals to that exponent times vector x0 in time now. Okay, it's like numbers, list of numbers. And then this is multiplication of two functions of s, which means when you convert it back, it becomes convolution of these variables in time, right? Because convolution will be transformed into multiplication in Laplace domain. We've seen that for transfer functions. So it will be convolution of inverse Laplace transform of that thing times b in the same order times u of t. We have convolution symbol here. This is actual explicit solution for x. And same thing, you can write that as integral, obviously. And this will be that type of solution. This is convolution integral plus some initial conditions state. Okay, this will be your x explicitly. People typically do not use these formulas for anything except theoretical proofs of different things. So we will not use it for anything. I'm just showing you that it's possible to write explicitly the solution of state equations. Okay, as that convolution integral, right? And same thing for the output. You just multiplying by c plus du. That's it. So you have actual explicit solution for the state equations to find y as a function of u. Pay attention, it's dependent only on matrices and on u. That's it. So the output y, you can write explicitly. Any questions on that? And this is purely theoretical part. I will mention for discrete case why we need that theoretical part and how you get additional intuition from the theoretical part, what that means. Because what I want you to pay attention to is the multiplication of that part by that part. The solution dependent on multiplication of that thing, which is series. You remember what exponent to the x is? As Taylor series. It's just powers of matrix A divided by all kind of constants, which are factorials of numbers, right? Remember that this is like infinite series, which is I plus exponent to A, blah, 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 all the things. Then like A squared, A squared, A cubed, all of these terms, right? So if you write them as just linear combination of terms here, all of them multiply B on the right. So you have like AB, A squared B, A cubed B, times some constants, right? This is how it will look like when you write that infinite series. So we will get to this terminology later, okay? That different powers of A times B and building some vectors out of it. Okay, you'll see that in discrete case much better than that. But this is where I'm going with that. All right, so this is discrete time case. If your system is discrete time, which means it has time steps, sampled system, all right? The representation is exactly the same. And I prefer indices of time to be in rectangular parentheses. And most of the textbooks are using that thing. But sometimes you see also representations where you have like subscripts here as index, like x of k plus 1 as a subscript k plus 1, okay? But since I'm using like subscript for dimensions, I don't want to mix them really. Okay, and this is the reason why I'm using like rectangular brackets for time index, okay? And these indices are all integers, which means k equals 1, 2, 3, 4, 5 natural numbers, right? For seesaw systems, again, this will be n by 1 vectors, this will be n by n matrix, this matrix will be n by 1, exactly the same thing like you have in continuous time. Same thing, all right? But the only difference that your transfer function will be in z instead of s. The variable will be z variable for discrete systems. To remind you that left shift in time, which is a pseudo derivative, like approximation of derivative, will be looking like that. So you have something related to initial conditions, and pay attention that we are typically using that only for a equals to 1. So for a equals to 1, the thing equals to 0 here, which means the only term you have here is x0, which is initial conditions, times z to the power of 1, right? That's all you have. So it's very similar to Laplace transform of single derivative in a way. So it's like z times z to the power of 1 because a equals to 1, right? It's like z times z transform of x minus initial conditions. Same thing with Laplace transform, right? So it's like when you're doing the same kind of manipulation, you get exactly the same thing. And you will get that type of formula. The only difference is that variable here name, right? Same formula here. You're just replacing S by Z. You get exactly the same transfer function formula. This is why I'm saying treatment of discrete time and continuous time are almost the same. Just replacing S by Z. This is the difference, okay? For stability, it will be a little bit different because we are talking about unit circle versus left semi-plane location for poles. But these are the differences, main differences, right? And what I wanted to mention is that the solution, the explicit solution, it will be series of different things related to matrices A and B and their powers, and input U. So if you write that explicitly, the solution for X, this is how it will look like. So any X at any given moment of time, K, will be equal combination of these vectors, because each one of them is vector. A to the power of K times X0 is vector, right? It's like n by n matrix times vector will be size of that vector, right? Another vector, but same size. Same thing here, A to any power times B and times scalar U will be that vector of the same size as vector B, which is n by 1, right? Dimensions of the matrix. So you will have A to the power of 0, which is what? What is A to the power of 0? Matrix to the power of 0. It will be I, identity matrix. Okay, it's like 1 in regular algebra. So it will be practically I times B, which is B. Second vector will be AB, then A squared B, A cubed B, and so on. So you'll have all the things added together, combined with numbers multiplying them. So it's weighted combination, it's practically linear combination of the matrices B, AB, A squared B, A cubed B, and so on, until the highest power. This is just linear combination of these things. All right, so far, this is what it is. Which means that any solution that you can get from solution of that kind of equation must be combination of these vectors. So if these vectors are not spanning the entire space, you cannot get to some space, some particular axis ever, no matter what your inputs are. Is it clear where I'm going with that? So any reachable point in n-dimensional space where you can get with your controls, with any control inputs, are spanned by these vectors, B, AB, A squared B, A cubed B, and so on. If you have some vector which is not linear combination of these vectors, you cannot get there with any U. All right? This is the thing. That these particular vectors are very important for us, and we will work a lot with these vectors because they tell you where you can get and where you can't get somewhere with any U. Because no matter what U you choose, you still will have linear combination of these vectors, right? For any U, any sequence of like numbers for your inputs. So no matter what input you choose for your system, it still will be linear combination of these vectors, nothing else. All right? Any questions on that? That's very important to remember. This is very important fact.
I have a
Yes.
question. When you said left shift in time, I was confused because you're talking about x of n plus a, which would be moving forward in time, which I would consider.
It's actually
shift.
backward.
X-
Why? Because you're adding something, x equals to 0 will be positive now. So you're shifting that way, which means the entire signal shifts back by that time. So it's left shift in time of the signal, not of the transform. Transform, you get positive. Like when you're adding constant in time, you're actually shifting signal to the left.
You're shifting
Because all of the values which
previously
were
to the left.
minus something becoming 0. So
I
you
see.
see,
I
it's
see.
like opposite logic in a way.
But okay, so if you were moving from n to n plus 1, you'd obviously be moving forward in time. But what you're saying is that the current equate,
It's shifting the axis, not the
it's
function.
shifting the axis, not the function.
Yes, it's shift of the coordinate system to the left,
Okay,
which for function means shifting to the right, but this is a terminology.
because we're in the plus space, that's true? I guess I'm
This is
like,
Z space, yes.
this is Z space.
So you're shifting the Z space to the left in time, the axis. Right?
Thank you.
Any other questions? Okay, MIMO systems are, again, not very different from CISO systems. We will not work much with them because it's more difficult by hand to write like multiple matrices, to multiply them, and to do all kind of manipulations on them. Formulas will be practically the same formulas. There are some like minor differences, but they are not nothing special. Just this matrix will have different dimensions. So B will not be vector. It will be given particular number of inputs M and particular number of outputs L. This matrix will be N by M. So M will be number of inputs. That will be a matrix now, right? For MIMO systems. This will be also a matrix, which will be L by N, which means number of outputs by number of states or order of the system, okay? And D will be a matrix. So D will be L by M, which is number of outputs by number of inputs. And this is why I'm saying that D defines actually the dimensions of the number of transfer functions that you will get, right? This is L by M. Now, Chi, if you are computing that formula, will be having elements I and J. So it also will be a matrix of L by M, right? And each one will then will have like cross links between different inputs and different outputs in the system. But here is a tricky thing. This is the most tricky thing to understand in MIMO systems in general. Even if each one of these particular subsystems or sublinks is stable, which means no matter what input you give to any of these inputs, all of these transfer functions are stable. So it's kind of matrix of stable transfer functions. The overall system might still be unstable because of the cross links between them inside. Okay, because of the interactions between different parts of the system. So each one of the like one-to-one connections is stable, but overall, when you're having multiple inputs, it still might diverge because each input can contribute in the same direction, kind of putting the output, which each one of them is stable, kind of, but overall is not. So you have all kind of issues with MIMO systems in terms of stability. It becomes more complex to analyze, especially when you get to nonlinear spaces and other more complex systems. So here we get to actual stability. And I will be talking about stability in terms of eigenvalues now, because we know that poles and eigenvalues are the same for us. So all we need to know is just to repeat the same theorems that I showed you for transfer functions. If you remember, for transfer function is stable if all poles are in the left semiplane for continuous time systems or in the unit circle for discrete time systems. This is what stability means. Yes. All right. I'm just replacing the name poles with eigenvalues and stating exactly the same theorem. All right. So if all of the eigenvalues of matrix A, and pay attention that for CISO or MIMO systems, A is still n by n matrix, same matrix practically, right? Regardless of number of inputs and outputs, A is still n by n, dependent on the actual physics of the system. So I'm just replacing poles by eigenvalues and claiming exactly the same theorems. This is what we have here. So if all of your real parts of the eigenvalues for your matrix A are less than 0, which means left semiplane, then it is stable asymptotically. Discrete time, same thing. If all of them are within unit circle, which means the absolute value of the eigenvalue should be less than 1. That's what it means to be inside of unit circle. Okay, their magnitude is less than 1. Any questions on stability? So it's pretty simple, straightforward, just copying the same thing. And now we can do example and see here. And we will solve one example for a particular system. We'll find stability of that system, transfer function, Bibo stability, ODE representation, zero input response, and I will write the system, since you cannot see it right now, I will write it on the board here. So we have matrix A, B, C. I assume that matrix D equals to 0, so we practically ignore that matrix in most cases for simplicity. And here are the matrices. It's interesting to see myself on the screen at the same time when I'm actually doing that. 0, 4, 1, 0. Matrix B equals to 1, 0. Matrix C equals to 1, -2. Okay. And I want to find asymptotic stability of that system. Is that system is asymptotically stable? Pay attention that this is exactly the same question that I solved online. Okay, and published. This is exactly the same system that probably you struggled through all the derivatives of y. If you remember, we tried to write that as transfer functions, and we needed to find all the ODE and all of the other stuff. It was complex. Okay, we needed kind of to find some tricks to get there. Okay, now it will become very straightforward. Okay, I'm just using formulas. To find asymptotic stability of that system, all I need to know eigenvalues of that thing, of that matrix. If they are in left semiplane, and I'm talking about continuous time system, okay. If they're in left semiplane, the system is stable, period. If not, they're not. Done. All right. So what is the characteristic polynomial of that matrix? So it's determinant of Si minus A. This is what I need to compute. And you can go and directly compute multiplying I by I, S by I, you'll get S, 0, 0, minus that matrix, then find the determinant of that matrix. Don't need any of it. Why? This is why. This is what I asked you to remember from linear algebra formula, the theorem. Okay, where the first coefficient in the characteristic polynomial, which is exactly the same. I mean, you can compute it and you'll get the same thing, but you don't have to. It's much easier. For second order polynomials, this is that easy. It's minus trace, which is what? 0. Trace is like sum of diagonal elements. So this one is 0. And what that thing is? Determinant of that matrix is 0 times 0 minus 4 times 1. It's minus 4. So it will be s squared minus 4, which is also s minus 2, s plus 2. You want to find the roots of the polynomial. So you have root at positive 2, and you have root at negative 2, which means is it asymptotically stable or unstable? It's not stable. It's asymptotically unstable. Because you have root at positive 2. It's unstable. You remember this would be exponent to the 2t. It's like that. Diverging. Okay, this will be the solution. Okay, so this is asymptotic stability. Now we want to find transfer function. Transfer function is relatively easy. You pick your methodology, how you want to find it. I will use, as example, just determinant divided by another determinant. Now, here I have determinant of Si minus A. Here I have determinant of logs Si minus A. Here, negative B, right? Negative B, C, D. Something like that. So pay attention that I know what that thing is already, right? This is that thing. I computed that already. Now I need to compute that space a little bit. So this will be determinant as I minus a. That will look like s minus 4. Second element will be negative 4, then minus 1, s, negative 1, 0, 1, negative 2, 0. These are the blocks. So as I minus 8 will be s minus that element. And then, wait a second. So Si minus A, it's not supposed to be like that. Hmm?
Second element.
So this is not supposed to be there, I think.
It should be S.
Should be S. It's minus 4 here. Yes, something like that. Because it's like you have S, 0, 0, minus 0, 0, 4, and 1. Okay. So now I need to compute it. The bottom part is still the same part. And here I'm developing that by the last column because I have a lot of zeros here. It's the most convenient one. So it will be negative 1, which fills that row and that column, times determinant of that thing, which is minus 1, s, minus 2. Because the thing will be s minus 2 divided by s squared minus 4. Okay. Now we can cancel some. It will be 1 divided by s plus 2. Which means that this is Bibo stable, but not asymptotically stable, right? So this is full transfer function. And this is exactly the same transfer function that we found before in the solved exercise online, right? This is exactly the same exercise. But now we found that just using technical formula, and you can use any of the 3 formulas that I gave you, you'll get exactly the same answer, right? Now, to get OD representation from that thing, now it's very easy, right? Pay attention, should you use that thing or that thing for OD representation? Because we have now 2 transfer functions, kind of. What is the right part to use? Now we want to get OD for that system. Are you using first order or second order system? Okay, what order your OD should have, which represents that system? Must be second order, which means you're using that thing. So what you actually say is that your transfer function, which is y of s divided by u of s, equal to s minus 2 divided by s squared minus 4. Now you cross multiply, if you remember how to get to ODE from transfer function. So you'll get s squared minus 4 times y of s equals s minus 2 times u of s. And now you think about multiplication by s as operator of derivative. S squared is like second derivative. S to the first degree is like first derivative. That's all you need. So it's y, 2 dots, plus, minus. Minus for y equals u dot minus twice u. That's your differential equation. Right? And after some experience, you can write that directly from here. Because pay attention that all of these coefficients are exactly the coefficients of that thing, right? Of the polynomial, characteristic polynomial. And all of these coefficients are exactly the coefficients of the zeros polynomial, right? We can write them directly. This will be derivatives of u, and this will be derivatives of y. Okay? Okay, now we have additional interesting question here. So given the system of equations, I'm giving you particular initial conditions. And given this particular initial conditions, I want to find solution of y as a function of t. Right? So I want to find the actual explicit solution to the function. We need some space here. Maybe remove some of the less important stuff. Okay, so here's what is given. We are given that y. Okay. So y0 equals to 1. And y dot 0 initial condition is -2. What is the solution of that equation? Generic solution of linear differential equation. We can write it explicitly. So y of t will be equal to c1 times exponent of -2t plus some other constant t2 exponent of positive 2t. This is homogeneous solution of that equation, right? And we are interested in zero input response, which means u equals to 0. This is a question. So I want to find that y of t, which means I need to find these coefficients, which will show you something very interesting here about bibostable and asymptotically unstable systems, right? So all we need to find is these coefficients. How do we find these coefficients? We just substitute initial conditions into them. So y0, which is 1, will be equal to c1 e to the 0 plus c2 e to the 0, which is c1 plus c2. This is the first equation, all right? For the second equation, we need to take derivative of y. So derivative of y is -2 times the same thing, plus 2 times the same thing. This is derivative of exponents. Remember that from calculus? Okay. So what we get here is that y dot 0, which is -2, will be equal to minus twice c1 e to the -2t plus 2c2 e to the 2t, all of that given t equals to 0. Right? So you get -2c1 plus 2c2. And this is your second equation. So -2c1 plus 2c2 equals to -2. You have two linear equations, obviously the single possible solution. So if you solve the system of equations, and you can solve that with multiple different tools, you can solve it by hand, you can solve it with network, you can use the formula or whatever you prefer. The solution will be like that. Okay. All of that is also inverted. It's interesting what Zoom actually will record because everything on that board is flipped like a mirror. All right. That's 1, 1, -2, +2 times C1, C2. I'm just solving system of equations equals 1, -2. I wrote the same system of equations as matrix equation. All I need is to invert that matrix and to multiply by that vector. So C1, C2 equals inverse of that matrix, which is 1 divided by determinant. If you remember, it's 1 times 2 plus 2. Switching between these two, which is 2, 1, -1, +2. When you multiply all of that, what you should get is 1, 0. Okay. So C1 equals to 1, C2 equals to 0. So what is y? This is what I want to find, right? So C1 equals to 1, C2 equals to 0. So the solution is done. How does it look like? This is explicit solution for y of t. This is definitely converging, right? This is exponent which is going to 0 very fast from some initial value. And the initial value will be obviously that thing to the power of t, which is 1, exactly as we wanted. And derivative of that thing will be -2 times e to the t will be -2. This is exactly that solution, right? But it's not asymptotically stable, but it is converging to 0. So what happens? So you need to remember that, yes, asymptotic stability is not telling you that it never can converge. The point of asymptotic stability is that for some initial conditions, it can diverge. This is what asymptotic instability is. Okay? So it's important that you remember that fact, that even asymptotically unstable systems can converge to for some particular initial conditions. Okay, you have initial conditions for which it converges, but not for all initial conditions. All right? Any questions on that? All right, so that's it for today. Thank you.